This is a review of the first part of Chapter 2 and also 6.2 that deals with conditional statements and also converses, inverses, and contrapositives. So a conditional sentence is if A, then B. We can form three new sentences. One is called the converse. When you form the converse, you switch or interchange the hypothesis and the conclusion. So in this case, this would be if B, then A. The inverse is negate. You take the opposite of the hypothesis and conclusion. This is all compared to the initial sentence, a conditional. So the inverse would be if not A, then not B. And the last one is called a contrapositive. And to form the contrapositive, we switch and negate the hypothesis and conclusion. So we start off with if not B, then not A. Another way to write a conditional is A with an arrow standing for implies. A implies B. So the same as if A, then B. If this sentence is true, then the contrapositive must also be true. They are said to be logically equivalent as far as their truth values are concerned. If the conditional is true, the converse and the inverse, they could be true or they could be false. You'd have to write it out and reason it out. But if one is false, the other is false. If one is true, the other is true. So they're either both true or they're both false. You will not have a situation where one is true and the other is false. So this is important and easy to remember. To disprove a conditional statement, if A, then B, we find what's called a counterexample. All you need is one example to disprove a sentence. You just find one thing. It could be a number, it could be a person, it could be a figure, depending on the sentence. A counterexample is where the hypothesis is true and the conclusion is false. So how I do this, if I have a sentence, if A, then B, I try to find something where the end is false. So I look for something where it is not B. I think of things that are not B, the opposite of B, where A still works, but that are A. I know that's vague, confusing, so I'm going to give you a concrete example. So if I have, if you are 15, then you are 18. So if I want to find a counterexample for that, how I do this, let me just write out counterexample. How I do this is I try to take the opposite of the conclusion. So the opposite of you're a teen is you're not a teen. So when I think who's not a teen, well, it could be someone really young, a 10-year-old, or someone above a teen, 20-year-old, or much older. So these are all things where the numbers where the conclusion is false, which is what I want. So I want to know, are any of these not a teen? Whether it makes the first part true, where they're 15. Well, a 10-year-old is not 15, so that doesn't work. A 20-year-old is not 15. I need that to be true, so that doesn't work. And a 6-year-old is also not 15. So none of these are good examples. So in this case, there is no counterexample. If there's no counterexample, then the statement is true. And by true, we mean always true. So let's now form the converse of that sentence, which would be teen. If you are a teen, then you are 15 years old. Right? Once again, we're going to try to find a counterexample. So how I start is, I look at the conclusion, and I take the opposite. So I want someone, the opposite of 15 is not 15. I want someone who's not 15, where the first part is true, who is, so the hypothesis, who is a teen. So can I think of someone who's not 15 who is a teen? And I can, of course. A 13-year-old is not 15, yet they are still a teen. A 14-year-old would work. Any teen not 15 would work. So any of these would be counterexamples. Something that would not work would be, for example, a 60-year-old. Even though a 60-year-old is not 15, of course they are not a teen. So 60 is not going to work for a counterexample. Once again, what's a counterexample? It's one specific thing where the hypothesis is true. So it's like the 14-year-old. So a 14-year-old is a teen, so that works. But where the conclusion is not true. So a 14-year-old, of course, is not a 15-year-old, so it is true-false. So a 14-year-old is a good example for a counterexample. Another concept we looked at was biconditional. And a biconditional, using a symbol, we can use a double arrow. It stands for if and only if. And a biconditional is formed if both the conditional is true and the converse is true. So if you look at this with the double arrow, we could read it as A implies B, or going right to left, B implies A. You put the two of them together, we have biconditional. And this could be written as A if and only if B. Or you could go the other direction, which I'm not going to write, but you could also write B if and only if A. You can also break down, so that's going from, if I give you a biconditional and I just ask you to rewrite it using the symbols, and then if and only if. But suppose if I give you if A then B, and if I tell you if B then A is also true, then you can form, if I ask you, so I give you two conditionals here, if I say write a biconditional, you could take either one and write A if and only if B. So you're basically just dropping the if and the then, and you're inserting the if and only if. Or you could have done B if and only if A. And the last thing to do is to review some logic. Suppose someone gives you a conditional statement, if A then B, and they tell you it is a true statement. And then they give you something else. And from that, you have to ask, is the statement any new conclusion that follows directly from the statement? So if they say if A then B is true, and someone just says, we'll assume that A is also true. So the question is there a new conclusion? Well, if A then B is true, and someone tell you A is definitely true, so if the first part is true, then our conclusion is we can write our conclusion is B. If A is true and A happens, then B is going to happen. Suppose someone gives you not A. Well, if you look at the first part of the sentence, if A and now not A, well, this right here is forming the inverse, because you're taking the opposite. Well, from what we said before, if the conditional is true, we don't know if the inverse is true, so there's no valid conclusion. So for this question, we would say no conclusion. Other thing I could give you would be B. Well, if I gave you the original sentence, if A then B, and I tell you B is true, well, I'm starting off at the end of the sentence, so I'm switching. That's the converse. Well, if the conditional is true, just like the inverse, we're not sure if it's true or false. So too with the converse, we're not sure if it's true or false, so no conclusion. We can't say anything for sure. And lastly, if I give not B, well, if I look at the sentence, if A then B, and I start off with if not B, that is the contrapositive. And the contrapositive is logically equivalent. It's truth value. So since the first one was true, we're allowed to finish off the sentence for the contrapositive. So if not B, we can say not A, and that is our conclusion. Actually, I'm just going to come to a couple other things. We know complementary angles are two angles that add to be 90 degrees. Supplementary angles are two angles that add to be 180 degrees. If x is the angle, then the complement we can write to that angle is 90 minus x. And the supplement to that angle is 180 minus x. And when we have word problems, there are a couple of different ways you can set it up. So for example, if I have an angle is 6 less than 3 times its complement, so this is method 1. Well, the angle, we use x is the angle, is in math means equals to. Is 6 less? Well, 6 less is you subtract 6, and 3 times the complement. Well, 3 times the complement is 90 minus x. So it's 3 with parentheses 90 minus x. So this equation is the angle is 6 less than 3 times the complement. An alternative way to do that is, well, complementary angles are two angles that add to be 90. So one angle is x. Well, think the other part. All of this is just saying really the other angle. So what do you mean about the other angle? It's 6 less than 3 times the first angle. So we do that. It's 6 less than 3 times the first angle. The only caution in the second method is x that you set up. Maybe it's the angle, maybe it's a complement, depending how people write things. In the first one, x is definitely going to be the angle. So sometimes you need to use common sense, check your answers, and make sure you're identifying the angle and the complement correctly based on the word problem. Then we have a concept of linear pair. Two angles form a linear pair. Right? Think of the term linear pair. There are two angles lying along a line. They're adjacent. So angle 1 and 2 form a linear pair. You need to know that term. And the relationship is they are supplementary. So angle 1 and angle 2 would add up to be 180, and that would be by the linear pair theorem if you asked to give a justification for that equation given the diagram above. And the last thing to look at, vertical angles. So if two lines intersect, we have 4 angles. The non-adjacent angles are called vertical angles, and they're equal. So, for example, angle 1, well, 2 and 4 are both adjacent to angle 1, so we don't choose that, so we choose the one across from it, angle 3. Angle 1 and 3 are vertical angles, and they are both equal to each other. In this example, you can see they both look to be obtuse. Seems reasonable that they're equal. And the other ones, angle 2 and angle 4, also are non-adjacent angles. They don't touch each other. And here they appear to be acute and are also equal. If you're given a diagram and you're asked to come up for a justification for those statements, then that is going to be by the vertical angle theorem. And something you're familiar with, just to mention, if two lines are perpendicular, then they form congruent adjacent angles. So if line M and line N are perpendicular to each other, then we know the measure of angle 1 is equal to the measure of angle 2, and they both equal 90 degrees. I hope this lesson helps, and review your notes.